Okay, welcome to this last lecture that I'm recording right now in my office. So, from the previous lecture video, you may see that we were covering the block diagram representations using the Z transform, which is not a complicated thing, and we have seen one example. Let me start by showing the previous example. This was the previous example where h of z, a Z transform, was given in equivalently three different ways. The first way was this cascade representation, or multiplication of 1 over 1 plus 1 over 2 z inverse times 1 over 1 minus 1 over 4 z inverse sort of thing, and that multiplication will induce one representation. There is also a direct representation where the numerator and the denominator may be written in z polynomials in its original form, or you can just write it in the form of addition of first order systems like this, and since they are added, they will induce a parallel implementation. The cascade implementation is quite easy because we have a first order system multiplied by another first order system in Z domain, which means the block diagrams must be in series. The direct implementation is the most interesting one, because if you have a denominator polynomial like this, then as you see, you will have Z inverse in the denominator and Z to the minus 2 in the denominator as well. Just consider multiplying this denominator with y of z, because that is equal to y of z over x of z. So if you multiply it with y of z, it means you're using y of z's delayed versions, which means multiplication by z inverse, and further delayed versions, and feeding them back and add them to x of z to form again 1 times y of z's standalone version. The parallel implementation is, as I say, quite easy. So I believe that the direct implementation, this one, is particularly interesting and difficult. So I will try to show you another example regarding the direct implementation. I hope this example will somewhat clarify things a little bit further. In fact, in this new example, we will have a numerator as well. So h of c is given as 1 minus 7 over 4 z inverse minus 1 over 2 z inverse, z to the minus 2, sorry, over, so this minus sign's position is here, and the denominator is 1 plus 1 over 4 z inverse minus 1 over 8 z to the minus 2. So it has, of course, a cascade form. It's a multiplication of two first order systems. You can find the parameters and also you can find the parallel form. Let me write the this is form 1, okay? Let's keep it in mind that way. So the h of z is also equal to, without making any calculations, I'm just going to write down the result for you so that you can check by yourselves. 1 plus 1 over 2 z to the minus 1. So from this point on, you see that this denominator has two roots, therefore the system has two poles. The first pole is at minus 1 over 2, the other pole is at let's write the denominator, and then you will see 1 minus 1 over 4 z to the minus 1, like this. So this is the second form, or the cascade form, you may say. And as you see, the second pole is now at 1 over 4. Okay. Now we will write it in the parallel form. which is the third form for your convenience, if you wish. It is a constant plus 5 over 3 over 1 plus 1 over 2 z inverse minus 14 over 3 over 1 minus 1 over 4 z inverse. And this is the third way. As you see, there is an interesting branch which is just the scaling by a factor of 4. Now I will focus to this direct form, and I'll try to draw it, you may say. So let me write it again so that I can use the equation immediately. So h of z is 1 minus 7 over 4 z inverse minus 1 over 2 z to the minus 2 over 1 plus 1 over 4 z inverse minus 1 over 8 z to the minus 2. And this is equal to y of z over x of z. Okay, you have to keep in mind this one. So x of z, as you see, will be multiplying the numerator, and y of z will be multiplying the denominator, and they must be equated to each other. And when you isolate a y of z, this one, which is multiplied by 1 at the left hand side of the equation, all the remainders will go to the right hand side, and that will correspond to the direct form. And the direct form will be like this. X, you can say x of n or x of z, whatever. The input comes into the picture, and there will be some feedbacks. Okay, I'm skipping some details here because you may first try to obtain the feedback portions which are with respect to the denominator. So y of z is multiplying that one, and that feedback portion will be here. Okay, the output, let's consider that we don't have any numerator for the time being. Okay, let's think of it like that. Then the output will be the delayed y of z, the delayed output multiplied by, as you see, we have a 1 over 4, so the scale here will be minus 1 over 4, because it will be on the other side of the equation with a negative sign. It will go, and it will be added to x, or x of z if you wish, and then another delay comes into the picture, z to the minus 2, like this, from here, and the scale of z to the minus 2 is minus 1 over 8, so it will be the negative of that, which is plus 1 over 8. So the feedback, the direct implementation, will look like this. But now we have the numerator. The numerator is relatively easy to understand, because as you see, the input has one branch which goes on as it is. There is x of z times 1 in the top left of the numerator. So we are using x of z as it is without any further amplifications. And then this x of z comes from this branch. Think of it that way. And it goes down here, and it must be multiplied by minus 7 over 4 to the right hand side, minus 7 over 4, and then it must be added to the result. But of course there is another z to the minus 2 term here, which is also multiplying x of z from the cross multiplication, and then we have its scale to be equal to minus 1 over 2. So the second delayed x will come here, and it will be multiplied by minus 1 over 2, and it will also be added to the result, and that will produce the final result here, which is y. You can say y of z, of course, since we are doing everything in the z domain. So this example is quite critical, and I'm sure that you will be able to understand or draw easily the cascade representations, which is in the second form, or the third form of parallel representations, where you have 3 branches and then you collect the branch outputs. They are not very difficult, but the direct implementation is the most interesting one, and I sincerely believe that I will ask something related to this one. Either you will have to draw the block diagram like this, or you will have to analyze this block diagram and come up with h of z in some way. So it can also be the opposite way around. As you see, the question can be like that. I can give you the block diagram like this, and then I can ask you what is h of z. Then of course you will write h of z like this, for example, for this question. The question may further go on like what is the cascade realization or representation. Then it will be in form 1, and then I can ask you what is the parallel form. Then you will have to say it's in the third form that we give here. So the questions may go in the other way around as well. That's quite a possible question. Let me be honest about that. Now, the block diagram representation business can stay here. The feedbacks will make they will change the positions of the poles, just like in the Laplace domain. So the stabilization process can also be considered. But we don't have the time to deal with that any further. I strongly recommend that you take a look at the book and the questions in the chapter of Z transform from the book before coming to the final examination. But for the time being, I will just try to introduce you something new, and I hope you will continue watching from here, because I don't think that I will ask any question regarding that, but this information is necessary for you. You have to be aware of the fact that there is also a bilateral, the unilateral version of the Z transform, just like the unilateral Laplace transform. This is just some information, and I will have to show you this. So unilateral Z transform is the new topic. It's a subchapter in this chapter of Z transform, and its existence or its representation is just like the unilateral Laplace transform. Do you remember what the unilateral Laplace transform was? The original Laplace transform, we know, is an integration from minus infinity to plus infinity. But the unilateral Laplace transform was an integral from 0 to infinity. So it was a different thing, and it required some initial conditions for the solution instead of the region of convergence, because the region of convergence is always out of the pole for the unilateral Laplace transform. Therefore, we don't need to indicate the region of convergence. The same situation is valid here. For the unilateral Z transform, it's always out of the pole, its circular region, because the unilateral Z transform is a summation. So x of z will be like this. It's some sort of a calligraphic x you can think of, just to indicate the difference, or you can say xu or something like that, to indicate that it's unilateral, not bilateral. It's single-sided, in other words. And the summation, as you may guess, starts from not minus infinity, but from 0, and it goes to infinity. And we have x of n, z to the minus n. Now, this is the unilateral Z transform, and we will see some examples where the unilateral and the bilateral, the previous original Z transform, are equal. For example, if x of n is already a to the n un, which forces our signal to start from 0 anyway, then the unilateral Z transform will be equal to the original Z transform, and that will be equal to 1 over 1 minus a Z inverse. And do we need to indicate that the region of convergence is radius greater than magnitude a? Well, no, we don't, because in the unilateral case, at least, we don't need to do that. It's automatically like that. So this was a simple example where the two Z transforms are equal. But in this example, as you see, things will be a little bit different. A to the n plus 1, u of n plus 1. So this u of n plus 1 starts from -1. So the signal starts from -1, and its unilateral Z transform will definitely be different from the normal Z transform. What was the normal Z transform? Let's start with that. The normal Z transform for this one was 1 over AZ inverse, the previous question, which is just delayed to the left hand side by some amount, and that will be, I suppose, Z over 1 minus AZ inverse. Yeah. So 1 over 1 minus AZ inverse is multiplied by Z, and multiplication by Z means you are shifting the signal to the left hand side. So this is the original Z transform with the same region of convergence, Z greater than A. But if you are talking about now the unilateral Laplace Z transform, then you will interestingly find this thing to be A over 1 minus AZ inverse. And as you see, these two are different. If you just make the summation, you will see that this is the answer. So the unilateral Z transform is sort of different. Now I will show you only one example, and then I will stop and load this video to the web page. The example that we will see requires the necessity of initial conditions for the solution of the systems. For instance, suppose that we have the system y of n plus 3y of n minus 1 is equal to x of n. This is an input-output difference relation, difference equation. Now we are going to solve this. By the way, this is a first-order system. As you see, we have one past sample of the output. And in order to find the impulse response of this thing, we need one initial condition. Just like the first order unilateral Laplace transform will require one initial condition. And in the Laplace case, we have the first derivative. Here we have a first delay. And that will be like this. I have to give a pause here, unfortunately. Okay, now I can continue. Sorry for the interruption. This initial condition will be not like y of 0 or the derivative of it at time is equal to 0, but it will be like this. We have this initial condition. Initial condition. Okay. So this initial condition, as you see, is the value right before 0, and that is given parametrically as beta, as you see. Now let's continue with this beta and how to incorporate this information into the Z transform of this whole expression. By the way, what was the Z transform of that? If you remember, it was y of z, y of n has a Z transform, y of z plus 3 times, in parentheses, in bigger parentheses, we have z to the minus 1, which is the delayed version of y of n, y of z, right? And that would be equal to x of z. But this is bilateral. Excuse me. Bilateral. The previous original case. Now this one will have to translate into unilateral like this. Be careful about what I'm doing. Y of z is y of z, of course. There's no problem about that. But this Z inverse shifted version will induce the utilization of the first initial condition like this, beta plus Z inverse y of z. So the value at n is equal to minus 1 must be incorporated into here like this. If you have further delays, then they will additionally put beta times z inverse plus alpha or something like that, which would correspond to the second initial condition, and that second initial condition will be at y of -2, for example. And those will be necessary if you have y of n plus y of n minus 1 plus y of n minus 2, for example. And now this will be equal to the input. Let us define an input here. The input will be just any input, because we are looking for a particular solution here. So the particular solution requires the knowledge of the input. It's not like the impulse. If it's an impulse, then this will be the impulse response, and we are going to use x of z is equal to 1. You can put it like that. But for the particular solution, we need an input as well, and I'm using this one, alpha times unit step. So this is the Z transform of unit step. Okay, so I'm applying alpha times u of n as an input. Now with these things we can solve for y of z. By the way, this is unilateral, so let me put it like this. The y unilateral z is equal to 3 times beta over, there's a minus sign, over 1 plus 3z inverse plus alpha over 1 plus 3z inverse in parentheses times 1 minus z inverse. Now this part that we have is the output without inducing any input. So that's a zero input response. Let's say it like this: zero input response, which is the homogeneous part. Whereas this one, this part is without considering the initial conditions or anything. So if beta is 0, for example, then it means we don't have any initial condition, or we can say that the initial condition is 0. That is called a zero state. The system was at 0 state with no initial conditions, or the initial conditions were beta is equal to 0. That would correspond to a zero state response, and that is also, as an analogy to the previous Laplace case, the particular solution, we can say. And from here on, what you really need to do is you need to invert this to find y of n. Okay. Invert and find y of n is equal to something. The inverse Z transforms of these things. And how do you find the inverse Z transforms, by the way, for the unilateral case? You don't really need to take the left-hand sided solutions or anything like that. Don't be confused. It's always the right-hand sided solution. It's always out of the poles. We have, as you see, 2 poles here. One of them is at z is equal to minus 3. The other one is at z is equal to 1. So it's out of 3. Radius out of 3. That's definitely a diverging signal. But nevertheless, that's the solution. You just need to invert these things. Now at this point, I want to stop, because although we have seen some examples about this unilateral Z transform, you will not be responsible from these anymore. So this is just an information for you to remember in DSP courses or things like that, just in case you encounter such unilateral Z transforms. Don't be surprised about that. It exists, and it requires the initial conditions, as you see. It's not very difficult, but it's out of our topic. So I will stop at this point, and I will load it as the last lecture for you. Hope that these will be helpful in your final examinations. I wish you luck and success in your final examinations. So this is a farewell, and I stop at this point.